Hello everyone, today we're talking about the workforce routing as the case study of route and optimization services. This course focuses on a real-world case study of workforce routing within field distribution operations. The aim is to demonstrate how routing optimization methods are applied in practical scenarios where multiple locations must be visited under operational constraints. Workforce routing is a critical component of efficient field operations. Effective routing directly affects travel time, resource utilization, and service reliability. By optimizing workforce routes, organizations can improve operational performance while reducing unnecessary travel and delays. Through this case study, learners will understand how workforce routing problems are defined, modeled, and solved using optimization techniques. The topic also aims to show how theoretical routing concepts are translated into practical decision-making processes in real operational environments. Workforce routing refers to the process of planning and optimizing the routes and schedules of field staff or teams who are required to visit multiple locations within a given time period. Unlike simple routing problems, workforce routing involves assigning visits to specific routes while also considering time and operational constraints. One key difference between workforce routing and basic routing is that workforce routing focuses on people rather than just vehicles. In addition to travel distance and time, factors such as working hours, service duration at each location, and workload distribution must be taken into account. These human-centered constraints add complexity to the routing problem. Workforce routing is commonly used in application areas such as field service and maintenance, inspection and monitoring activities, and last-mile or on-site service operations. These scenarios highlight the need for optimized routing solutions that balance efficiency, feasibility, and service quality. In workforce routing scenarios, field distribution operations typically involve daily on-site visits to multiple locations within a limited working period. These operations must be carried out using a fixed number of personnel and resources, which places significant pressure on planning and scheduling processes. When routes are planned manually, several challenges often arise. Visit sequences may be inefficient, leading to unnecessary travel and time loss. Workloads may be unevenly distributed among staff, and estimated arrival times may become unreliable, affecting service quality and customer satisfaction. As operational complexity increases, manual planning becomes insufficient. Optimization is needed to systematically evaluate routing options, balance workloads, and ensure that field operations are carried out efficiently and consistently. This context forms the basis for applying routing optimization techniques in workforce routing scenarios. Field distribution operations face several operational challenges that directly affect routing and scheduling decisions. One of the primary challenges is time and scheduling constraints. Field staff typically operate within limited daily working hours and must adhere to fixed appointment times or service windows at different locations. Resource limitations further increase complexity. The number of available staff or teams is often limited, and individual workers may have different skill levels or availability. These constraints make it difficult to assign visits efficiently while maintaining balanced workloads. Service reliability is another major challenge. Inefficient routing can lead to delays, missed appointments, and inaccurate estimated times of arrival. These issues negatively impact service quality and customer satisfaction, highlighting the need for optimized workforce routing solutions. Workforce routing models rely on several types of input data to accurately represent real-world operations. These inputs include the geographic locations to be visited, along with information about field staff or vehicles responsible for performing the visits. Accurate location data is essential for reliable routing calculations. Time-related data is also a critical input. This includes working hours, availability of field staff, and defined time windows for visits. In addition, the service duration required at each location must be specified, as it directly affects scheduling and route feasibility. To simplify modeling and enable effective optimization, certain assumptions are often made. These may include the use of a single depot or starting point, predefined visit locations, and a fixed planning horizon such as a single working day. Clearly defining input data and assumptions is essential for interpreting routing results correctly. Modeling workforce routing problems requires translating real-world field operations into a structured routing model. This process begins with representing the road network as a connected graph, where locations are linked through network paths with defined travel times and distances. Routing costs are then defined based on key performance measures such as travel time and distance. At the same time, operational constraints are incorporated into the model. These constraints may include working hours, service durations at visit locations, and availability of staff or resources. The optimization objectives guide how routing decisions are made. Common objectives include minimizing total travel time or distance, balancing workloads among field staff, and ensuring that all routes remain feasible and realistic. By combining network representation, cost definitions, and constraints, workforce routing models provide a structured foundation for effective optimization. The traveling salesman problem, commonly referred to as TSP, is a classical combinatorial optimization problem. Its objective is to determine the most efficient sequence for visiting a set of locations exactly once while minimizing a total cost, such as travel time or distance. TSP is characterized by its simplicity and focus. It is typically calculated for a single vehicle, team, or field staff member and does not include capacity constraints. The main decision variable in TSP is the order in which locations are visited, making it a sequencing optimization problem. In workforce routing, TSP is particularly relevant for scenarios involving a single field worker or team that must complete multiple visits within a working day. Understanding TSP provides a foundational step toward modeling and solving more complex workforce routing problems that involve additional constraints or multiple resources. The solution process for the traveling salesman problem follows a structured workflow. The first step is matrix calculation, where travel time and distance values are computed between all visit locations. This matrix provides the cost relationships required for the optimization process. The second step involves sequencing optimization. Using the matrix data, the routing system determines the most efficient order in which locations should be visited. The goal is to minimize the total routing cost while ensuring that each location is visited exactly once. In the final step, the optimized visit sequence is converted into an actual route. This includes generating navigable paths on the road network and producing timing information such as estimated arrival times. Together, these steps transform abstract optimization results into practical routing solutions that can be used in real-world workforce operations. Time windows define the periods during which visits can start or must be completed at specific locations. These constraints are common in workforce routing scenarios, where appointments, opening hours, or customer availability restrict when services can be performed. Service duration represents the amount of time required to complete the task at each visit location. This time must be accounted for in routing calculations, as it directly affects the total duration of a route and the ability to meet time window constraints. Together, time windows and service duration significantly influence workforce routing decisions. They affect visit sequencing and determine whether a route is feasible within the available working hours. Incorporating these factors ensures that optimized routes are not only efficient but also operationally realistic. While the traveling salesman problem is useful for simple workforce routing scenarios, it has important limitations. TSP assumes that all visits are performed by a single vehicle, team, or field staff member and does not account for capacity or workload constraints. As operational complexity increases, this assumption becomes unrealistic. Many real-world workforce routing scenarios involve multiple staff members or teams, each with limited working hours, different skill sets, or specific resource requirements. In such cases, assigning all visits to a single route is not feasible. When workload distribution and resource allocation become necessary, more advanced routing models are required. These models extend beyond simple sequencing and allow routing decisions to consider multiple resources, making them better suited for complex workforce operations. The vehicle routing problem, commonly referred to as VRP, is an extension of the traveling salesman problem designed to handle more complex routing scenarios. Unlike TSP, VRP involves multiple vehicles or field teams that operate simultaneously from one or more starting points. A key characteristic of VRP is that it generates multiple routes at the same time. These routes must respect capacity and resource constraints, such as working hours, maximum workload, or the number of visits assigned to each team. This makes VRP significantly more flexible than TSP for real-world operations. In workforce routing, VRP is particularly relevant for scenarios involving multiple field teams or staff members. By distributing visits across several routes, VRP supports balanced workloads and enables more realistic and scalable routing solutions for complex field operations. Choosing between TSP and VRP depends on the characteristics of the workforce routing problem. One of the primary decision criteria is the number of available staff or teams and the number of locations that must be visited within the planning horizon. TSP is suitable when a single field staff member or team is responsible for completing all visits and when there are no capacity or workload constraints. In such cases, the main challenge is determining the optimal visit sequence. VRP becomes necessary when multiple staff members or teams are involved. When capacity limits, working hours, or workload balancing must be considered, VRP provides a more appropriate modeling framework. Understanding this decision logic helps ensure that the routing model accurately reflects real operational conditions. Workforce routing involves constraints that are directly related to human resources rather than vehicles alone. One of the most important constraints is working hours. Field staff operate within defined daily working time limits and are often required to take mandatory breaks, both of which must be respected in routing plans. Task and service-related constraints also play a key role. Different visit locations may require varying service durations, and some tasks may require specific skills or qualifications. These factors affect which staff members can perform certain visits and how routes are constructed. Workload balancing is another critical consideration in workforce routing. Assigning too many visits to a single staff member can lead to fatigue and reduced service quality. By balancing workloads across teams, routing solutions support sustainable operations and improve overall efficiency and staff satisfaction. This case study focuses on a daily workforce routing scenario within an urban environment. Field staff are required to visit multiple locations during a single working day, and routing decisions must account for travel, service, and scheduling constraints. The scope of the case includes a defined number of visit locations and field staff members operating within a limited planning horizon. All routing decisions are made for a single operational day, reflecting typical real-world field service operations. The primary routing objectives in this case study are to minimize total travel time and distance while ensuring that schedules remain feasible. In addition, workload balance among field staff is considered to support efficient and sustainable operations. This case provides a practical example of how workforce routing models are applied in real operational contexts. Before optimization, workforce routes are often planned manually using personal experience, local knowledge, or simple heuristics. While this approach may work for small-scale operations, it typically lacks a systematic and data-driven foundation. As a result, several inefficiencies can be observed. Travel times and distances tend to be longer than necessary, and workloads are often unevenly distributed among field staff. Some staff members may be overloaded, while others are underutilized. These inefficiencies introduce operational risks. Delays may occur, appointments may be missed, and estimated arrival times become unreliable. This situation highlights the limitations of manual planning and creates a clear motivation for applying routing optimization techniques. After applying routing optimization, significant improvements can be observed in workforce routing outcomes. Visit sequences are optimized systematically, resulting in shorter total travel times and reduced travel distances compared to manual planning. Resource utilization also improves as workloads are more evenly distributed among field staff. Working hours are used more efficiently, reducing idle time while avoiding overloading individual staff members. These improvements lead to better overall operational performance. Arrival times become more predictable, service delivery becomes more consistent, and the organization gains greater control over daily field operations. This demonstrates the practical value of applying optimization techniques to workforce routing scenarios. Routing optimization has a direct impact on both operational efficiency and sustainability. By reducing unnecessary travel and improving visit sequencing, optimized workforce routing leads to shorter travel times and distances, which increases daily operational productivity. Cost and resource savings are another important outcome. Reduced travel distance leads to lower fuel consumption and operational costs. These savings can be significant, especially in large-scale or recurring field operations. From a sustainability perspective, optimized routing contributes to reduced emissions by minimizing fuel usage and travel-related environmental impact. By improving efficiency and supporting more sustainable workforce operations, routing optimization aligns operational goals with broader environmental objectives. Interpreting optimization results requires a focus on key performance indicators that reflect operational performance. Common indicators include total travel time, total travel distance, and on-time arrival or service completion rates. These metrics help evaluate the effectiveness of routing solutions. Decision support outputs provide additional insights beyond basic metrics. These include route feasibility, compliance with working hours and time windows, and indicators related to staff workload distribution. Together, these outputs offer a comprehensive view of operational performance. For managers and decision-makers, these results support data-driven decision-making. By identifying bottlenecks, inefficiencies, and improvement opportunities, routing optimization results can be used to refine operational strategies and improve workforce management. This case study highlights several important lessons. One key takeaway is that routing optimization improves both efficiency and service reliability. Another important lesson is the critical role of data quality and well-defined constraints in producing realistic and effective routing solutions. The approaches demonstrated in this case study are transferable to a wide range of sectors and operational contexts. Workforce routing optimization can be applied to various industries, including utilities, maintenance services, inspections, and logistics. Scalability is another important consideration. The methods discussed are suitable for both small-scale operations and larger, more complex workforce routing scenarios. This flexibility supports future expansion and adaptation to changing operational needs. In this topic, we explored a real-world case study of workforce routing and demonstrated how optimization techniques can improve field operations. The case study showed that workforce routing benefits significantly from systematic optimization rather than manual planning. By applying models such as TSP and VRP, routing problems can be structured and solved effectively, leading to improved efficiency, balanced workloads, and more reliable service delivery. These approaches support better operational planning and decision-making. This case study illustrates how theoretical routing concepts are applied in practice. By bridging theory and real-world applications, workforce routing case studies provide valuable insights into the practical impact of routing optimization.